A parallel plate capacitor consists of two metal plates, each of area A and separated by a distance d. When the plates of the capacitor are connected to a battery, one of the plates is given an excess charge plus Q, and the other is given an excess charge minus Q. Due to this, a uniform electric field is created between the plates of the capacitors. Towards the edges of the plates, we observe fringing in the electric field. That is, the field is non-uniform when the plates of the capacitor are separated by some distance. We know that d is the distance between the plates. But if d square is very less compared to the value of the area A, the fringing effects can be neglected in the regions which are far off from the edges of the plates. Let the magnitude of the charge density be sigma for the plates with a charge Q on them. Then, sigma is equal to Q by A. Let this be equation 1. Let us assume the region on the left side of the capacitor as region 1, region between the plates as region 2, and the region to the right side of the capacitor as region 3. Let us now calculate the electric field in the regions 1, 2 and 3 with respect to the capacitor. We do this by applying the Gauss law to calculate the electric field in the regions 1, 2 and 3. We know that for a uniformly charged plane sheet of charge, the electric field strength E at some distance away from it is equal to sigma by 2 epsilon naught. Let this be equation 2. We use this result to calculate the net electric field strength in regions 1, 2 and 3. In region 1, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the left. We also see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the right. Hence, in region 1, the net electric field strength E naught is equal to sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0, since the two electric fields are oppositely directed. Now let us look at the region 3. In the region 3, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. We see that due to the negative plate of the capacitor, the electric field strength E is also equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the left. Hence, in the region 3, the net electric field strength is equal to plus sigma by 2 epsilon naught minus sigma by 2 epsilon naught, which is equal to 0. Since the two electric fields are oppositely directed in region 3 as well. Now let us look at region 2 between the plates of the capacitor. In region 2, we see that due to the positive plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed away from the positive plate and towards the right. We also see that due to the negative plate of the capacitor, the electric field strength E is equal to sigma by 2 epsilon naught, and directed towards the negative plate and towards the right. The region 2, which is in between the plates, has two electric fields of equal magnitude, sigma by 2 epsilon naught, which are both pointing towards the right. Hence, in the region 2, the net electric field strength E naught is equal to sigma by 2 epsilon naught plus sigma by 2 epsilon naught. On simplification, we get E naught is equal to sigma by epsilon naught. Let this be equation 3. Let the potential difference between the positive and the negative plates be equal to V. For a uniform electric field of strength E between the plates of the capacitor, we have V is equal to E naught D. Let this be equation 4. Substituting equation 3 in 4, we get V is equal to sigma D by epsilon naught. But we know that the charge density sigma is equal to Q by A. Therefore, we have V is equal to QD by A epsilon naught. Let this be equation 5. Now, capacitance of a parallel plate capacitor C is equal to Q by V. Let this be equation 6. Substituting equation 5 in 6 and simplifying, we get capacitance C is equal to epsilon naught A by D. Let this be equation 7. This expression for the capacitance shows that the capacitance is directly proportional to the area of the plates A and inversely proportional to the distance between the plates. We know that the capacitance of a capacitor not only depends on the geometry of the plates, the distance between the plates, but also depends on the dielectric medium between the plates. When there is no medium between the plates, let the potential difference between the plates be V naught. The electric field strength be E naught and let its capacitance be C naught. We know that the capacitance C naught is equal to Q by V naught. Let this be equation 8. The electric field strength E naught is equal to sigma by epsilon naught. Let this be equation 9. The capacitance C naught is equal to epsilon naught A by D. Let this be equation 10. After disconnecting the charging battery, let a dielectric medium fill the intervening space between the plates of the capacitor. The dielectric medium in between the plates will be now in the presence of the electric field in between the plates. We know that when a dielectric medium is in an external electric field, it is polarized. The net effect on the dielectric is that there is an induced positive charge density plus sigma dash on the right face and minus sigma dash on the left face. Due to this, there is a weak induced electric field, say E dash, in the direction opposite to that of E naught. Since the dielectric material has lesser number of free charge carriers as compared to the metal plates, which are conductors. Then, according to Gauss' law, the electric field strength E in the dielectric will be E is equal to sigma minus sigma dash by epsilon naught, which is less than the magnitude of E naught. The potential difference between the plates V is equal to ED, which now becomes V is equal to sigma minus sigma dash into D by epsilon naught, and hence V is less than V naught. In the case of linear dielectrics, sigma dash will be proportional to the external electric field strength E naught. But since E naught is equal to sigma by epsilon naught, it implies that the value of sigma minus sigma dash is proportional to the sigma value. Or, we can say that sigma minus sigma dash is equal to sigma by K, where K is a constant of proportionality which is called the dielectric constant of the medium. Since the electric field strength E is less than E naught, and hence potential difference V is less than V naught, this clearly implies that the value of K must be greater than 1. For any dielectric medium other than air, K is greater than 1. Using sigma minus sigma dash equal to sigma by K in the expression for V, we get V is equal to sigma d by K epsilon naught. But since sigma is equal to Q by A, we have V is equal to Qd by AK epsilon naught. Therefore, the capacitance with a dielectric medium is C dash equal to Q by V. Here, it is of importance to note that since the charging battery is disconnected, the charge on the capacitor remains constant even after the introduction of the dielectric. Now substituting value of V in the expression for C dash and simplifying, we get C dash is equal to K epsilon naught A by D. Here, the value of K epsilon naught is called epsilon, where epsilon is called permittivity of the medium. For air, the dielectric constant K is equal to 1. Hence, we have epsilon equal to epsilon naught for air. For dielectrics other than air, we have the dielectric constant K greater than 1. The dielectric constant K of the medium is defined as the ratio of the permittivity of the medium epsilon to the permittivity of the free space epsilon naught. We know that C naught is equal to epsilon naught A by D. Hence, we can write C dash is equal to K C naught. Since K is greater than 1 for any medium other than air, we have C dash greater than C naught. We can also write K as the ratio of C dash to C naught. Thus, the dielectric constant K is a dimensionless quantity and has no unit since it is a ratio between similar quantities. Dielectric constant is also called as the relative permittivity of the medium and is also denoted by epsilon r. K is also known as the factor by which the capacitance increases when a dielectric medium fills the intervening space between the plates of the capacitor. Therefore, we see that by introducing a dielectric medium between the plates of the capacitance of the parallel plate capacitor increases.